Welcome to Pomodoro Joe for Sunday, March 19th, 2023. Today we're doing LeetCode problem 211, Design, Add, and Search Words Data Structure. It's a medium problem. So this says, design a data structure that supports adding new words and finding if a string matches any previously added string. Implement the word dictionary class. Word dictionary initializes the object. Void add word adds word to the data structure. It can be matched later. Bool search word returns true if there is any string in the data structure that matches the word, or false otherwise. Now this is the important part. Word may contain dots, where dots can be matched with any letter. I'll say that one more time. Word may contain dots, where dots can be matched with any letter. So in the example here, they'll add bad, dad, mad, pad. Then when they do a search, they can search for bad, or they can search for .ad, which will return true because there's pad or mad. They can also search for b ... which will return true because bad matches. All right, this is going to be tricky. We'll put 25 minutes on the Pomodoro timer and get started. So if you've been following my videos this week, you probably remember the trie. That's the data structure called trie, T-R-I-E. So the trie data structure is sort of a multi-branched tree where each node represents a letter in a word, and all of the connected nodes represent the next possible letters. So for example, with T-R-I-E, you'd have one node that would be a T, and it will connect to R, and that will connect to I, and that will connect to E. But then we also need some special ending character so that we know we've reached the end of a word. So we'll have, I like using /0. So you have some ending character to let you know you've reached the end of a word. And for example, if you had something like tree, you'd basically start with that same T node. Let's see if I can do this. Yeah, you'd start with the same T node, and you'd actually start with the same R node. Let's see if I can figure out a way to represent that. So you'd have the same R node as well. But then you would reach a new node, which would be an E, and that would lead to another new node, which is an E, and then that would lead into a new end node. Okay, so we will try to implement something like a trie for this word dictionary class. It's going to be a little bit tricky because we have these dots that can represent any character, so we'll have to treat those specially. All right. Let's get started. So we need to have some storage, and for the trie, we went with a dictionary. So we'll have an empty dictionary as our base storage. Now the key in the dictionary will represent the letter, and the value will represent the next level of characters that we can reach. So that will be another dictionary. So essentially this is a dictionary of dictionaries. So again, the key will be the letter, the value will be another dictionary, and the key in that dictionary will be the next letter in our word. So this would look something like, let's see, this would be So for the word trie, we would have the key T, which leads to another dictionary that has the key R, which leads to another dictionary that has the key I, and that leads to another dictionary that has the key E. And now if we add another word, like tree, then we'll have the same T, the same R, but then this one will split and it will have two entries. One will be an E and the other will be an I, and they will lead to two different dictionaries. Let's see if I can do this. So they will lead to two different dictionaries, but each of those dictionaries has the key E. And of course, we'll still need to lead to our end dictionary, which will be our special end character. So it'll look something like this. This is not a great representation, but the basic idea is a dictionary where every letter in our word is a key into that dictionary, and every value is another dictionary where the next letter will be the key and the value will be another dictionary. Okay, so here we'll start out. Actually, I'll just leave this in. Okay, so we'll have some basic dictionary that starts as an empty dictionary, and that's our data. And then we'll have some special end character here. This can be anything, but I like using this. All right, now in our add word, we will start with some basic data that starts as our self.data. Then for every character in our word, we need to make sure that we have an entry in our dictionary. And if we don't, so if character is not in our data, then we'll create a new entry, which is just going to be an empty dictionary. You can think of data as the current level of your word. So if the character is not at our current level, we'll create a new entry in our dictionary for this character, and we'll set its value to be an empty dictionary. And then our data will become this new level. So we basically go down to the next level or advance to the next letter in our word. And at the very end, we still need to add our final end character. And for this, we can set the value to be anything, but I like to set it as an empty dictionary just to keep consistency in our entries. So that's all we need to do for our add word. Now our search word, this is where it gets particularly tricky. So normally, if you're just looking for the word, you could do something where you're just looking at every character, following the paths down our data structure until you get to an end character. So you could do something like this. All right, so if we were just looking for the words, ignoring these special case dots, you could say for every character in the word, if the word is not in the current level of our data that we're looking at, then we can just return false. This word does not exist in our try. Otherwise, we set the data to be the next level in our word or the next set of characters that are connected to this root character. And we can keep going until we've reached the end. And at the very end, we don't just return true. We need to return whether or not that this data has our special end character. So this would work if we didn't have these special case dots. However, because we have the special cases, this doesn't quite work. We need to have some special handling of the dot characters. So for this, I'm actually going to create a helper function. So in our helper function, we'll take the word, but we'll also take the current index into the word. And you'll see why we do that in a second. And then we'll take the current data that we're looking at. So what level of our try are we looking at? Okay, so let's grab all this because we'll just be modifying it. And let's modify this here. So our search now, we'll just call our search helper. And we'll return the search helper passing in, let's see, we have to call self dot because this is an instance method. And we'll pass in the whole word, and we'll pass in our base data as the starting point. Okay, so this will work for all the non-dotted words. But now for dotted words, we need some special handling. So for every character in our word, if character is a dot, well, we'll need to do something special. For now, I'm just going to pass and continue. So what do we need to do if it's a dot? So if the character is a dot, then we'll need to grab all of the potential options. So every key in our dictionary at this level could be an option. So remember, the key in our data represents the character at this level, and its value is a dictionary of all the options or all the other characters, all the next characters that we can get to. So if we have a dot, that means that this could be any character. So any one of our potential characters or keys in this dictionary at this level, so in our data, is potentially a path we need to follow. Okay, so for this, we'll have to say for every key, let's do that. So if the character is a dot, then we can say for every key in this data's level, this could potentially be the character we're looking for. So we'll just do a recursive call here. Okay, so this is where it gets tricky. We need to do a recursive call, but we don't want to pass in the entire word. We want to pass in the remainder of the word. So in this case, we can't just say for every character in word, we need to keep track of what index we're at. So for that, we'll have to say for, let's see, for I or index and character in enumerate. So enumerate will go through every character in the word, and it will return both the index and the character itself. And so the index will be I, the I plus 1, because the character is the dot. So we need to go from the word at I plus 1 to the end. And the data that we're going to be passing will be data for this key. So I'll go over this again here. So we have this helper function. It's going to take a word. It's going to take, actually, let's skip the index. Let's make it easier on ourselves. We'll skip this for now. It'll just take a word and the data, which represents the level in our try that we're at. Okay, so let's do some base cases. Since this is going to be a recursive call, you can see here. Let's do some base cases. All right, so if we have a word, but we don't have data, that means we can't have a match, so we'll return false. So if we have no word, all right, so our first base case says we have a word, but we don't have any more levels in our try. Then we can return false. There's no way this word is in our try. The next case is if we don't have a word. So if we don't have a word, then we need to do this one down here. We need to basically return, did we have the end character at this data level? If that's true, then we are fine. If it's false, then this word doesn't exist in our try. All right, once we pass the base cases, then we go through every word, and let's see. This now will become word from I plus 1 to the end. All right, I'll go through this again, I'll go through slower here. So we've made it past our base cases. We have a word and we have some data, which is whatever level we're at in our try. If we have a word but we don't have any data, then we're done. We have to return false. If we don't have a word, then we have to check to see if at this level we had a potential end of word. And so we check for the end of character at this data level. Okay, now for the majority of our cases, we're going to have some word and we're going to have some data. So we're going to go through every character in our word. If the character is the dot character, then we have a special case. We have to go through every key in our level because this dot could represent any character. So our characters are the keys into our data structure. So we'll check every character in our data and we'll do a recursive call. If we find the rest of the word at the next level for this key, then we can return true. We've found it. Finally, if we check every key in this level of our try and none of them match, we don't get any trues, then we can return false because we know we've exhausted all the possibilities for this level of our try. So that's how we handle if it's a dot. Now, if it's not a dot, let's see, and I'll put a continue in here because we don't want to fall through and check if it's in the data. Okay, if the character is not a dot, then we'll check to see if it's in our current level of the data. And if it's not, we'll return false. Otherwise, we will advance to the next level of our data. And finally, we'll do the same thing we were doing before. If we reach the end and we don't have an end character, we'll return false. Otherwise, we can return true. I know this one's super confusing. I would totally recommend take a look at this code. I'll post it on my GitHub. The link will be in the description. Check it out. Let's see if this works. All right, let's see. Misspelling here. Try that again. Okay, it seems to work. Let's see if we can pass all the tests. All right, and we pass, and it's not too bad. We beat 64% for runtime and 84% for memory. All right, now if you want to stick around, we got a couple minutes left on the Pomodoro. I will show you a really cool, simple trick that we can do to improve our runtime significantly. And it has to do with these constraints. So we have word lengths between 1 and 25. Because our word lengths are constrained, we can actually create different tries for every single length of word. That only means we have to have 25 different tries, which isn't that bad. Then we can exit early, and we can also reduce the number of possibilities just based on the word length alone. So how do we do that? Pretty simple. We'll say we have more than one data. We have datas. So these are our different tries. And we'll make 25 of them. So we have 25 empty dictionaries. These will represent different tries for different lengths of words. Now here we can say data is self.datas at length of our word. So this reduces essentially how many entries are in our try, because they're all going to be the same word length. And then down here, this will be data self-datas for length of the word. And that's it. So we have 25 different tries. We'll just use the one try that matches the length of the word that we're looking for. Let's see if this works. Still seems to work. Let's see if it gives us any boost in our runtime. Oh, I need to do 26. because it's 0 indexed. That's my apologies. Let's try that again. And we have a huge gain. Now we're at 99%. We're beating 99.89% of all others for runtime and 82.7% for memory, which is awesome. Anyway, I think this is pretty awesome. We're out of time. Check this one out. I'll leave links in the description. You can check it out on my GitHub. You can play around with it. I'd recommend studying this one. This part in particular can be tricky. Check this part out. Really try to understand how this works. All right, hope you enjoyed this. Hope you had fun. Hope you can go out and write better code.